Okay, I think everything's good. So welcome everyone to our first GeoSeminars by GeoLatinas series in English. We also have seminars going on in Spanish and people's theses and things like that. So make sure to check that out. I'm going to share my screen so you can see the lineup that we have upcoming, as well as to introduce our speaker. Is the screen share working? Okay, great, because I don't see there's usually the little glowing thing around it. Okay. So here is our lineup. I believe it's every 2 weeks for the next couple of months. This is our winter season. All right, so to introduce today's speaker, we have PhD candidate Maria Cristina Figueroa, and she's a geochemist and current PhD candidate at the University of California Riverside in the Department of Earth and Planetary Sciences. She received her BS in geology from the University of Puerto Rico, Mayagüez, and her research focuses on investigating the links between marine biogeochemical cycles and mineral deposits. She is currently wrapping up her doctoral degree, a journey filled with multidisciplinary collaborations that led to joining research cruise expeditions, interning at NASA JPL for 3 years, and applying reactive transport modeling and machine learning techniques to geochemical data sets. All right, so I'm going to stop the screen share and Maria Cristina, take it away.
Great, thank you so much for that wonderful introduction. Let me just go ahead and share my screen. Right, hopefully you can see it. Yeah, so I wanted to start off by just talking a little bit about myself. So I'm just basically going to reiterate my bio that was just described. So I completed my bachelor's in geology from the University of Puerto Rico in Mayagüez, which is also my hometown where I was born and raised. During my undergrad, I developed interest in marine geochemistry, and I became very interested in pursuing research in marine geochemistry. So after my bachelor's degree, I decided to go straight for a PhD. And so currently I am a PhD candidate at the University of California Riverside, where I am working with Tim Lyons. So Tim Lyons, this person right here, who is demoing in the lab. So I was very fortunate to be able to work with him. He gave me freedom to choose the research topics that I was interested in marine geochemistry. So that led to a lot of really good collaborations and field work and cruise expeditions, as you can see from these figures here. Like was mentioned previously, I also did an internship at NASA JPL, where I worked on developing pyrite as a biosignature and also incorporated some machine learning to my data set. And so now I am in the process of finishing my PhD. And so this talk is basically a mini version of my dissertation talk, where I am going to go over the main projects that I've been working on. And so I want to start by talking a little bit about the evolution of atmospheric oxygen through time. So throughout Earth's history, the atmospheric oxygen levels have slowly increased, not really in a linear manner, but more of an episodic manner, right? So from the very start of the planet's formation, so from a highly reducing atmosphere to the widespreading of the oceans and continental configuration, life started to slowly emerge, especially photosynthesis started to emerge, which gave rise to oxygen levels until the atmosphere was able to hold more oxygen. And so these oxygen levels are intrinsically associated with oxygen levels in the ocean. Right, so in the ocean, we see a similar oxygen chemistry configuration. So if we look at the time period before the Great Oxidation event, we see that our oceans were mainly ferruginous. So ferruginous meaning that they were anoxic or depleted in oxygen and iron rich. So these ferruginous oceans correspond to an iron-dominated redox due to low sulfate levels in the ocean. And these are periods where iron banded formations formed, for example, as you can see from this picture here. Now, as time progressed and oxygen levels rose, we were able to get more sulfate into the oceans by weathering and river outflow. So more sulfate into the oceans meant that the oceans became sulfitic, or euxinic, another word for sulfitic. So these were sulfitic oceans dominated by anoxia and high hydrogen sulfide rich environments. But then with the rise of oxygen to levels similar to the levels that we have today, the oceans became oxidized. And so we have the modern ocean today, which is oxic, and it's highly hospitable to many forms of marine life. However, when we go back to the rock record, we start to see that things are a little bit more complicated. And so here in this figure, right, so below we have a schematic depiction of the evolving ocean redox divided into surface, mid-depth, and deep ocean. So we can see how the surface became more oxidized with time, with the increase of oxygen in the atmosphere. We can see that the deep ocean took a little bit longer to keep up, but the interesting and complex chemistry occurs at mid-depth. So we can see, for example, that the ocean can experience oxic, euxinic, and ferruginous conditions during the same time period. And so this is a question of bistability and depositional systems, but it also brings the question of, are these related to global oxygen levels, or are these other factors that lead to the redox makeup of these depositional systems? And so a good way to try to tackle these kind of questions is by taking a closer look at the proxies that we use to reconstruct the past. So now various proxies are used to reconstruct the past, specifically the proxies for paleoredox reconstruction that look at certain species that are redox sensitive. And by studying their characteristics, we can infer the redox chemistry of the environment under which it formed. So by now, I've thrown the word redox around maybe about 100 times. But just to clarify, when we talk about redox, we are mainly concerned about how oxidized or reduced the system is. And so why do we really care about redox? So redox is actually very important as it influences major factors in the ocean and in the sediments. So for example, redox influences biogeochemical cycles, right? So how a chemical travels around and changes around in a system. It also influences organic matter accumulation and also influences the sediment chemistry. So the early diagenetic processes that take place in the sediments, and this is really, really important because it influences burial. And so what gets buried, it's what gets recorded in the rock record. So some of the redox proxies that we use, one of them here, for example, is the iron proxy or iron speciation. So iron is a redox sensitive element. So during early diagenesis, iron is cycled between reduced and oxidized forms and can react with other redox sensitive elements such as sulfur to form pyrite. And so this redox looks at different iron minerals through a series of extractions, and it takes a closer look at these reactive species and creates important ratios where we then can plot our results to see what kind of ocean chemistry was present at the time of formation. Another proxy is the iron proxy. So the one that looks at rhomboidal pyrite size and distribution. And this can be a useful proxy because pyrite forms in reduced environments, and its occurrence and size can give information about its environment. And so to give a brief overview about the ocean chemistry today, so we know that the ocean is oxygen rich. The water contains a lot of oxygen, which is great for life to thrive. There's plenty of sulfate that makes its way to the sediments. Whereas iron is variable, and this is because iron is important for primary production. So areas that have a lot of primary producers consumes a lot of iron. However, as a geochemist, I am mainly concerned about what happens in the sediments. So those early diagenetic processes that take in these chemical species and how they react together and how they change from being oxic to anoxic. And so I'm mainly interested in species related to sulfur, to carbon and iron, and how they interact in the sediments to ultimately form pyrite. Now here are a few of the research sites that my lab has worked on. So places like the Black Sea and foam, these are classic environments for proxy calibrations. So the Black Sea, for example, it's a classic euxinic site, and foam is a classic oxic site. However, I'm more interested in places that do not follow these traditional biogeochemical processes. So for example, the Santa Monica Basin, which experiences seasonal variability. And so these variabilities can affect oxygen levels, which will affect the biogeochemistry and the redox chemistry. And also the Saanich Inlet, which is a highly variable site, highly variable system that can experience anything from oxic to euxinic conditions. And so for this talk, I am going to focus mainly on the Santa Monica Basin. So the Santa Monica, it's located in California, and it's part of the California continental borderland region. And so there are sills and ridges that they impede the bottom water circulation. So at the deepest part of the basin, right here where we have MUC9 and 10, these bottom waters are nearly anoxic. So they have very low amount of oxygen, but it's still not zero. It's not completely anoxic. But it's a really reducing environment. And because of that, the sediments there are laminated. As we can see from this image here, we can see laminations, changes in colors. And so these laminations make these sediments ideal for investigating biogeochemical parameters at a high resolution. And ultimately, what we found out from the Santa Monica Basin is that it is an exceptionally iron-dominated system. And for that, it's a very, very interesting system. So here I'm showing the iron speciation data for this basin. So I'm showing data from the slope and also from the basin, but we're mainly interested in the basin because this is where the chemistry gets really interesting. So what I'm showing here in the data points in blue correspond to highly reactive iron. So highly reactive iron is the iron that can react to form other species. It ultimately can form pyrite. And then in white, we have the pyrite that is forming out of this highly reactive iron. So commonly what we see is that as the highly reactive iron decreases, pyrite formation increases, right? As we can see in the slope, right? Highly reactive decreasing to form pyrite. But when we look at the basin, we see that this relationship does not exist, right? We see that there's very high elevated amount of highly reactive iron, but very little pyrite forming. And when we plot the data points here, we see that the basin sediments, so the ones in warmer color, they lie all the way down here, where some of them lie around ferruginous oceanic conditions, right? Which we know that it's not correct. And so to take a closer look at the iron speciation, here I have a figure of the iron mineralogy within the sediments of the basin sites. So mainly what I want to show is that the highly reactive facies here correspond to iron oxides. So the deep blue one corresponds to the very reactive or labile iron oxide. So these are usually the iron oxide forms that react really quickly. So we usually just see them right below the sediment water interface, and then they get consumed. However, here we see that they persist throughout the sediments. And the same is true for the more crystallized form of iron oxides, which is a strange occurrence because these sediments are anoxic. So we would expect these oxidized iron facies to get reduced and consumed, but that is not happening. And just to show how crazy this data is, I am comparing it to Saanich Inlet data. So, and this is from a site that has a very similar bottom water chemistry to the site in the Santa Monica. So what we see here is what we normally find in reducing sediments, which is that the main highly reactive iron fraction is pyrite, right? The one in yellow. Whereas in the Santa Monica, we see the complete opposite. So it looks like in these sediments, there's just not enough sulfide. So then the question became, why don't we have enough sulfide in these sediments? And we came up with two possible factors. So one of them being that maybe these sediments have a cryptic sulfur cycle. And what I mean by that is that maybe the sulfide that is there is getting oxidized back to sulfate by sulfide oxidizing microbes. So for this, we did 16S RNA sequencing, but we were not able to find any sulfide oxidizers. So then we discarded this hypothesis. And then our second hypothesis was that maybe these sediments have recalcitrant organic matter. So meaning that the organic matter that is there has been reworked into an unreactive phase. And so this organic matter is just not reacting with sulfate to reduce the sulfate to sulfide. And so this is the one that we are gonna look at. So to figure out if the organic matter was recalcitrant or non-reactive, we looked at the organic matter itself. So we looked at the carbon and nitrogen in the organic matter, and also the radiocarbon in the organic matter. So here on the left, we have carbon isotopes from the organic matter and carbon to nitrogen ratios. We're mainly interested in the basin sediments, which are the red data points here. And mainly what we found here is that from the basin sediments, there is some evidence of episodic turbidites, but mainly these sediments are composed of marine source organic matter. And there seems to be a degree of reworked organic matter, but not too much. However, when we look at the radiocarbon data, so the warmer colors here, we do see some interesting things here. So for example, in the core top sediments, we see that they appear to be much younger than the deeper sediments. So much younger corresponds to more reactive organic matter, whereas in the deeper sediments, it significantly shifts to older organic matter, right? So this means that near the surface, there's young reactive organic matter, but below it, there is not. Then we also did another method on our samples, which is the Mossbauer spectroscopy method. And this is a method that directly analyzes the samples without the need to do chemical extractions. And we can get a lot of data on the iron mineralogy. So we did this method to be able to compare it against the iron speciation, which is a method that destroys the samples. It extracts, it does chemical extraction, so it destroys the samples. So we just wanted to compare them. But in doing this method, we also got a lot of very interesting data. And so I just want to show one of the main findings. So the main finding was the detection of iron oxides bounded to organic matter. So there seem to be these iron oxide organic matter complexes in these sediments. And so this is a really good finding because these complexes, what they do is that they stabilize iron oxides and organic matter. So you have the iron oxides coupled with organic matter, and they're both protecting each other from reacting with anything else. And so from previous findings, we know that the organic matter in these complexes, they can remain bounded to iron oxides for up to 1500 years. So it's a really great way to preserve organic matter, right? It enhances organic matter preservation. And it also enhances iron oxide preservation. So this explains why these sediments are rich in iron oxides, because they're stable there and they're not reacting with anything else. And it also explains why the organic matter is not really reacting with anything. And all of the chemical processes are happening near the sediment water interface, where we're getting delivery of younger organic matter that can then react. And so we did reactive transport modeling on these sediments as well to get further quantify the chemical profiles, the reaction rates, and the fluxes in these sediments. So on the left, we have the measured data that we use to fit the model. And on the right, we have the remineralization pathways, so the main electron accepting processes. So I'm not going to go into too much detail about what this means, but I just want to show that the most important thing to see here is that most of the reactions, so most of the remineralization pathways and chemical reactions are occurring in the shallow portions of the sediments, right? So here, for example, remineralization is occurring up to maybe 5 centimeters depth. And the same is true for these other chemical profiles, where we see the greatest amount of change occurring right above 5 centimeters, and below that, very little to no change occurs. And so this aligns with our Mossbauer data and our organic matter data, that it's just the very shallow sediments that are doing all the work, and anything below it is not reacting with anything. And so here I have a conceptual model that explains this a little bit better. So this conceptual model is explaining the chemical zones within the early diagenetic sediment depth. So only the first 5 centimeters. So these arrows here, they correspond to the fluxes of iron. So the reduced iron leaving the sediments and the oxidized iron entering the sediments. So these fluxes are really high fluxes. So it means there's a lot of iron in this system. And also an interesting thing to note here is that this system holds a lot of iron oxides and a lot of reduced iron, which is not very common. Like usually you have one or the other, but this one has both. So the main pathway occurring here is a pathway called the sulfide mediated iron oxide reduction, right here, where we can see it occurring here. So just in its most simplest form, what we're seeing is that because we have so much iron oxide in this system, the iron oxide can react with sulfide, hydrogen sulfide. They can react, and what they're doing is that the sulfide is oxidizing to sulfate, and the iron oxide is getting reduced to dissolved iron or ferrous iron. And so this draws sulfide levels lower and enriches iron levels further. And so this is all happening within that shallow sediment depth. And this process of continuously recycling of iron species, it's what's creating these iron and organic matter complexes. So it's what's enhancing this preservation of iron and organic matter. And also a very important thing to note here is that this is possible. So the presence of iron oxides and reduced iron, it's possible because of the very specific oxygen levels in this system. So this system, the bottom waters, they experience oxygen levels from 4 to 10 micromoles. So they never reach zero, it never reaches anoxia, and it doesn't become more oxidized. So it's just at this perfect level where you can have both reduction and oxidation happening together, and it just fuels this very strong iron cycling between these species. So it's a continuous cycle between iron oxide and reduced iron that creates this very enhanced iron dominated system. And so just the main takeaways. So this system shows a very unusual diagenetic pathway for modern marine sediments. And in this pathway, it's producing iron oxide and dissolved iron enrichment. And it's also producing iron carbonates and iron silicates, which I did not go into detail, but they do occur in these sediments. And so this is very interesting because these iron minerals, they are mineral precursors and constituents of Precambrian iron formations, right? These were the minerals that were found during these banded iron formations. And so it's just very interesting that we have a similar chemical system occurring in a modern depositional system. And so it just brings the question of, is this an underappreciated diagenetic pathway that is occurring in other modern depositional systems? But also, what about ancient marine systems? Like it could be that we have misclassified some of these ancient banded iron formations into thinking that they were forming in ferruginous waters when maybe it was other factors contributing to their formation, at least for the iron formations that formed not too long ago during appreciable amount of oxygen levels. And so that brings me to the end of the Santa Monica project. But now, and this is the last slide, I just wanted to introduce another project that I worked on and that I am still developing. And so it's on looking at the chemistry of sedimentary pyrite. So I did previous work where I found that by looking at sulfur isotopes and trace metals in pyrite, so doing in situ analysis of sulfur isotopes and trace metal in pyrite, we can create a very strong classification system using machine learning algorithms such as random forest and cluster analysis to be able to predict pyrite origin types. So this is very um, useful for biosignatures, for example, and also for paleoredox as well. And so the results were very encouraging because we were able to classify sedimentary pyrite into diagenetic stages and also secondary alteration. And so, I mean, this is by itself very interesting, and it shows that it's a promising use as a proxy and possible biosignature. So yeah, well, the main takeaway is that now moving forward, I am adding more samples to this data set, specifically more modern samples, because this data set is mainly made up of hydrothermal pyrite and metamorphic and magmatic pyrite, and the sedimentary pyrites are mainly older pyrite. So I'm adding more modern pyrite samples, such as the ones that I collected from Saanich. And also something that I'm doing is that I am investigating why is it that trace metals are such a good proxy for paleoenvironmental reconstruction? Because I was able to find that trace metal in pyrite, it's a really good indicator for paleoredox. And many previous studies have found the same, but no one has been able to clearly identify why this is the case. And so that's what I'm currently doing. And then that brings me to the end of my talk. And so here is a list of all the people that I'm grateful for, that they have been able to help in my research in one way or another. All of the funding agencies. And yeah, here's my email address if anyone wants to contact me. And I'm open to any questions. Thank you.
So for the people who are listening on Facebook, you can leave questions in the comments, and Carlo will read them, or you can ask in the chat if you're in the Zoom meeting.
Hola. I have a question. Is that okay if while we wait for people to ask? Well, first of all, I would like to congratulate Maria for a very nice presentation. This is not my area of expertise, so it is, something that I normally don't listen in industry. I do exploration offshore Mexico. So it's nice to see, this kind of research that is done. And I would like for Maria to kind of reiterate, why is this research important? We can see that we're trying to understand environments and it's part of our planet that we have to take care. So I would like, for Maria to, in her own words, why is this, very detailed analysis and research important?
Yeah, no, that's a very, very good question. So sadly, I'm not battling climate change. I'm not making any progress that can directly affect our lives, but I'm more looking into how we interpret the rock record, right? So I'm looking at what are the proxies that we're using to reconstruct the past, and what are some things that we are maybe missing or overlooking, right? So a very big debate when we are reconstructing the past is whether the samples that we're using, if they have a global implication, or if these rocks come from a system that is closed and the chemistry in those rocks are influenced by local chemistry instead of global. And so that's why when I showed the map of the places that we are looking at, we're not really looking at the open ocean, but we're looking at more enclosed marine environments that are direct, that have more of a local effect, to point out some of the possible pitfalls of the proxies that we use. So for example, the Santa Monica Basin is a perfect example of this, because it's localized, and in being localized, it has a very different chemistry from the open ocean. And so we just want to make awareness that when we're interpreting these rocks from the past, that way we may be looking at something that is localized rather than global.
That is great. Thank you so much. Great research.
Hi, Maria Cristina. There's no questions here in the Facebook chat. Okay, there's a question over there.
Yeah, thank you so much. Congratulations, Maria, on your work. It is really informative. I just have a question on the samples. You had like 2 samples from 2 different settings, like the basin and slope.
Mm-hmm.
And if you are reconstructing the past environment or the oceanic environment, which of course we know that it has been changing, like the current basin was the ancient slope.
Mm-hmm.
So how do you link that, like in your geochemical cycle, like conclusion? Thank you.
Yeah, no, that's a great question, and that's mainly beyond the scope of what I do, because I look mainly at modern settings and early diagenetic settings. But the geochemists, that they look at deeper time when they're looking at the rock record, for example, they have to do a lot of analysis, such as dating the samples so that they get an absolute age on them. And they also do certain ratios, like iron to aluminum ratios and so forth, to get a better sense of the timing of the deposition of that section in the rock record. And so you can plot it very nicely, and you can see those changes and infer if it was like, when was it formed, and if it was part of the slope, and how sea level influences that chemistry that you see. I don't know if that answers your question.
Yes, I understood. Thank you so much.
Okay, there's just one comment on the Facebook chat box that I would like to read. This is from Emmanuel Munoz. So proud of what Maria Figueroa has accomplished with this topic, making it easy to understand with this presentation. So this is from Emmanuel Munoz, Maria.
Thank you, Emmanuel. He's a friend since kindergarten, so a friend for life.
How amazing.
Yeah.
He's watching on Facebook.
So I just want to remind all the people that is watching that if there's just another question, you can just email to the Gelatina's email or Maria's email that it's here in this this slide.
There is a new question.
There's a new question here in the chat box. I am curious. This is from Eva Baranski. Sorry if I've just pronounced. I'm curious to know if, given the condition of the process, how common do you think this process is in modern settings?
Yeah, so that's a great question, and that's something that we've been thinking about. So there are definitely sites that are also iron dominated in modern environments. So for example, the Argentine basin is iron dominated. and has a similar chemical setup to the Santa Monica. The Chile coast has similar iron-dominated systems. So there are iron-dominated systems in the modern. The Santa Monica just happens to be heavily enriched compared to the other ones. But if we think about climate change and we think about how that affects oxygen levels in the ocean, right? Whether it decreases oxygen levels and creates more hypoxic environments like this one, maybe in the near future we can start to see the development of modern settings that are similar to this one.
Thank you.
Okay, so
I actually have another question. I think if that's okay. You mentioned turbidites, and I got excited at that point because more excited because that's what I do when I do exploration. I look for turbidites that have been deposited, millions of years ago. These are going to be our reservoirs, and that's something that I do. I map in the subsurface. You mentioned that it's a marine source. So you mean that the turbidite flow started along the slope? I mean, it's not coming from a delta or a river or something like that. So I just
Yeah,
wondering.
no, so yeah, that's a fantastic question. And so yeah, I do have to clarify that because these turbidites are episodic. And so if you look, maybe I can go back. If you look at the basin, making here, right? So there's a steep slope and there are canyons around here, and this area is California, which is tectonically active. So these turbidites are these episodic events that they bring in a lot of terrestrial input, right? So we can see from, where is it? Here. These turbidite data points, they fall all the way down here, which corresponds to mainly terrestrial organic matter and reworked organic matter. So they are coming from the slope. These are not the marine source. When I mentioned marine source, I meant everything else besides the turbidite. It's formed from the marine fall in the water column that makes its way to the sediments.
Oh, okay. I missed that. Okay, that's awesome. Thank you so much.
May I ask another question if you don't mind, Maria?
Yeah, of course.
Yeah. It's just, I'm curious, like how sensitive is the samples which you are taking, because it's just 1 meter. Like, how do you handle them to make sure that there is no contamination? Like the data which you are going to get, the results are going to be like accurate, because 1 foot is, yes, you understand.
Yes. So when we sample these sediments, we put them, I have pictures here. Let me see. Right, so this is how we sample the sediments in these polycarbon tubes, and we seal them right away so that these sediments are not exposed to oxygen, right? So these are anoxic sediments. So we need to keep we have to keep that same environment for them. So we seal them very quickly. And then when we're in the lab, we have to extract them in an anoxic environment. So mainly we use argon or nitrogen to keep that environment, to keep that atmosphere reduced so that these sediments are not exposed to oxygen, because once they're exposed to oxygen, chemical alterations can occur. And so we make the extraction process, like this is For example, this is how I would do it in the field when I'm in a cruise expedition. I have this glove bag, and inside is where I handle all of those sediments. So I make sure that the air here is reduced and there's no oxygen in it. And that's how I take out the sediments and I extract them to later analyze them. And so we just reduce any contamination on them that way.
Yeah, that's super cool. Thank you.
Okay, Maria,
Okay.
there's another question, I think, in the chat box from.
Okay. Okay, yeah, I
So,
see it.
thanks, Maria, for great talk. I'm wondering if you have distinguished geomechanical variation in the CA phosphates.
No, I do not. I have not looked at phosphates. I do think that phosphates have been looked at in the past. There are a few papers from the 1990s that maybe they did look at that, but I'm sorry, I have not.
Okay, thank you. So I don't know if it's anyone has another question here in Zoom, or there's no other question in Facebook. So
I have a question. Really
okay,
quick.
Daniel, go ahead.
Hi. Thank you, Maria, for a great talk. I was just curious. I mean, I think it's really impressive, the variety of like geochemical and analytical techniques, as well as the machine learning you've done in the course of your PhD. I was just curious if you could talk a little bit more about how, I don't know, your experience, your background, and like how you kind of got into doing geochemistry, but also the machine learning, because you mentioned a lot of different tools you've used, and I thought it was really cool.
Yeah, no, thank you so much for that question. Yes, I have done a lot of different things throughout my career. Mainly it's been through active collaboration. So that's something that my lab is really good at. And that's a benefit of getting an advisor that is more on like the senior stage of their professional process, right? That you get to collaborate with a lot of good people. So for the machine learning specifically, this was a collaboration with a former postdoc that he spent most of his PhD collecting trace metal data from pyrite. And so we, like in my first year, we started talking about his data set and how we could add sulfur isotopes to that data set and maybe look for ways where we can do some classification or statistical analysis to see how we can develop a biosignature. So it was mostly through conversations and then finding the right people to talk to that have the expertise in those subjects. So we were lucky to find those people that helped us to develop the machine learning algorithms and techniques. So it's just mainly through active collaboration and just not being scared to ask people for help.
Thank you.
And also I should say that the Geoladinas, they did have a machine learning course that I did attend. It was at 5 a.m. for me, so it was hard to attend, but I did go to at least 3 or 4 of them. So it's good to be aware of what Geoladinas is offering, because they're always very, very helpful. And so things like that machine learning course that they were doing really helps people like me to learn more about these techniques and apply them to their research.
Okay. Thank you so much once again, Maria. So is there another question? No, it is just a couple. Okay. So Vanessa, if you just want to continue.
Yes, I wanted someone, if we could stop your screen share and I'll share my screen. We wanted to show you our certificate that we'll be giving you for doing this talk. 1 second, it's still loading. Yeah, thank you so much for doing, especially the first talk of our seminar series. We were so happy to have you speak, and it was such a great talk. And you can see it's like signed by everyone who organized it. But we were so happy to have you here, and thank you so much for doing it.
Thank you so much. This is awesome. Thank you.
And we'll send you the certificate afterward. But we would just want to recognize the great work that you did in organizing and doing this talk. And then we want to invite everybody to follow us on social media if you haven't already. We're quite active on Twitter, especially. I haven't used Facebook much, so I don't know how often we use Facebook, but you know, it's we do our Facebook Lives for these GeoSeminars. So it'd be really great if you follow us. And I think that this talk will also be posted on our YouTube channel. So you can, anyone who's watching can view it there as well. And thank you all for coming and for asking great questions to our speaker. And yeah, thank you.
Gracias. Thanks to the host.
Thank you, everyone.
Your Latino show. Eric is from
Thank
Tanzania
you.
and he's in India, so we're international.
Yeah, thank you so much. Thank you so much. It was great, like, to participate in this. I hope I will join again in the
Next one.
in the coming talk. Yes, it was really nice. Thank you so much.
Okay, I will stop the live stream and the recording.
Maybe we can take a
Okay. Good night. Good night. I don't know.